Okay, I'm going to talk about the Poisson distribution. And the Poisson distribution describes a sort of event such as follows. Suppose you're standing near a waterfall. Imagine Niagara Falls. And you're standing some distance away from the waterfall. And every once in a while, a drop falls on your nose. Not every minute, not every second, but every once in a while. Now there are many, many drops that fall over the waterfall, and only a few of them land on your nose. This is the type of situation that's described by the Poisson distribution. So let's unpack these words. It evaluates the probability of a number of independent, infrequent occurrences out of many opportunities. So for instance, when I just talked about the water falling over the waterfall, you could say every droplet has an opportunity to hit my nose, but it doesn't happen frequently. Okay? There are many, many examples of physical situations like this, and we'll give a few more examples later on. So I talked about infrequent opportunities within a period of time. You could also talk about infrequent occurrences within an area. Suppose you're a new archer and you set up a target 200 yards away and you keep shooting arrows. Now if you're not an experienced archer, you probably won't hit the target very often. This is because the area of the target is a very small fraction of the area where you can shoot the arrow. Now, so hitting the target becomes a very infrequent event. Now you can do the same thing with these different scales, and we'll see more examples later on. Okay. So each event has a very small probability. There are some examples on page 210. When I just talked about archery, the probability that any single arrow hits the target is very small. So the Poisson distribution comes into play when n is large, n being the number of trials. So when I'm talking about shooting arrows, that would be the number of arrows I shoot. And p is small. P is the probability of any particular arrow hitting the target. In my example of water going over waterfall, n would be the number of water droplets going over the waterfall, and p would be the probability that any individual water droplet hit my nose. So here they're saying p is small, something like 1 out of 100. If the probability of the event is large, say 1/2 or 1/3, then the Poisson distribution doesn't apply. You need to find events such that each individual event is very infrequent. But altogether, out of the many, many possibilities, it's quite common to have one of these events happening. Okay, here is the mathematical expression for the Poisson distribution. Now we have this new quantity lambda that we haven't defined yet, and I'll explain what lambda is below. Lambda is the mean number of occurrences in the given unit of time, area, volume, etc. So lambda equals np, where n is the number of trials and p is the probability of occurrence. So let's give an example. Suppose I shoot 200 arrows at a target, and suppose I have a probability 0.01 of hitting the target with any given arrow. Well, that means 200 is the number of trials, so 200 is n. 0.01 is the probability that any one trial will be successful, so that's p. So after 200 trials, then lambda is the mean number of arrows that I expect to hit the target with. So that's going to be 200 times 0.01, and so that's equal to 2. Okay. Out of 200 arrows that I shoot, I expect to get roughly 2 arrows in the target. No, I may get more, I may get less, but on average I'll get 2. Now the number e down here is this mathematical constant. You should have seen this in your calculus class. And here they point out that that lambda, which is np, is both the mean of the Poisson distribution and the variance of the Poisson distribution. Okay. Now let's see how we can apply this formula. Okay, so for an example, let's go back to our example. Think of the arrows. I shoot an arrow 200 times, and the probability that any arrow hits the target is 0.01. So I'm going to compute what's the probability that no arrows hit the target in 200 trials. That's going to be P of 0. Probability that no arrows hit the target in the 200 trials that I conduct my experiment. Okay. So what's P of 0? Well, I'm going to use this formula. My lambda is going to be equal to 2. We already saw that. Okay. So here I'm going to have 2 to the x, so that's 2 to the 0, times e to the minus lambda, so that's e to the minus 2, divided by, now it turns out that 0 factorial is equal to 1. So that gives me e to the minus 2, which is roughly 1/8. If I was going to do p of 1, that's going to be equal to, well, my lambda is equal to 2, so it's going to be 2 times e to the minus 2, same as before, divided by 1 factorial. So that's equal to 2e to the minus 2. Okay, so the probability of 1 arrow hitting the target is somewhat more than 0 arrows hitting the target. Now I could make a table, as we talked about discrete random variables. We could talk about the number x and p of x. So I've done the first two. I've done I've done x equals 0. I've done x equals 1. Okay, x equals 0 was e to the minus 2. X equals 1 was 2 times e to the minus 2. And I could continue to do this table using this formula, just plugging in different values of x, 2, 3, 4, etc. Okay, an additional example here. Here they're talking about infrequent occurrences per distance. Suppose you have an average of 3 striped trout per 100 yards. What's the probability of seeing 5 striped trout in the next 100 yards, assuming a Poisson distribution? Now, why is this a Poisson distribution? Because the probability of seeing 1 trout in 1 yard is 3 out of 100. That's my P. And here I'm looking at 100 yards. Here my N is equal to 100. Okay. So now if I look at the next 100 yards, I'm going to be using the same P and the same N. Okay. So P times N is lambda, and you can work that out. That's actually going to be equal to 3. Okay, so that's where they get this formula from. The probability that you see 5 striped trout is going to be used the same formula that we used before. Plug in 3 for lambda, 5 for x, and you get this number, about roughly 1 out of 10. Okay. Here's a variation of the problem. How about in the next 50 yards? Well, in this case, P is still 3 out of 100 because we still have the same situation with the trout. We have an average of probably 3 out of 100 of seeing a trout in a single yard, but we only have N equals 50. We're only looking at 50 yards. So that gives me NP is equal to 1.5. So that's why they put 1.5 here in for lambda instead of 3. Now, as mentioned a couple slides ago, the Poisson distribution is a variant of the binomial distribution. Here's another variant of the binomial distribution called the hypergeometric distribution. In the binomial situation, each trial was independent. For instance, the usual binomial situation is like rolling a die, and counting the number of ones that you roll, say in 10 rolls. In that case, the probability of rolling a 1 is equal to 1/6 for each roll. But we can have other situations that are slightly different. For instance, when drawing cards from a deck. All right. Now, if you want have independent trials, you can draw cards from a deck and you replace the drawn card each time. That way you can draw the ace of spades in 2 consecutive draws. But if the card is not replaced, then each trial depends on the previous trial. These are called non-independent trials. And in this case, you can use the hypergeometric distribution. So we'll see the details in the next slide. Okay, so in order to understand this, let's keep in mind one particular example. let's suppose I draw a bridge hand of 13 cards. So I'm going to draw 13 cards, and I'm going to count the number of spades. The number of spades in my hand of 13 cards. All right, so let's see if this situation fits this particular rubric here. So I'm randomly draw little n elements from a set of big n elements without replacement. Okay, now does that fit my particular situation? Well, yes, it does. I've drawn 13 cards. My little n is equal to 13. And I've drawn it from a set of big N elements. Yes, that's true also. I've drawn it from a deck of 52 cards. Without replacement, that's true, because when I draw a card, I don't put it back in the deck. So this works for my current situation. So assume there are successes and n minus r failures in the n elements. Okay, so I can talk about the probability. Rather, what that means is I need to look at my 52 cards and determine how many of them count as a success, how many of them count as a failure. Well, if I'm looking for spades and I say spade is a success, that means in a deck of cards there are 13 successes, and there's going to be 52 minus 13, or 39 failures. Okay, so the hypergeometric random variable is the number of successes x drawn from the r available in the n selections. Okay, so every time I draw cards, I'm going to get a different number of spades. That's why it's a random variable. And I can get a formula for the probability of the number of spades being different values. Now in this case, be a little bit careful. Here I draw n equals 13 elements. That's the size of my bridge hand. That's the number of cards I draw. Here it just so happens that the number of successes is equal to the number of cards in the hand. That's not always going to be true. For instance, suppose I wanted to count the number of kings that I draw in a hand. In that case, n would still be 13, but r would be 4. So keep little n and little r straight. Little n is the number of draws that I make. Little r is the number of possibilities for success out of a total of big N elements. Okay, so given all our quantities, this is the formula for the probability of x. All right, x is the number of successes in the n elements. So in our particular example, number of successes would be the number of spades. And again, that's going to vary from hand to hand. These are all fixed parameters though. N is the total number of elements. In our case, it's 52 cards. R is the number of successes. That's going to be 13 spades. N is the number of elements drawn. That's 13 cards in a hand. Okay, so I'm just going to plug these numbers into this expression here. And remember, R choose x means r factorial over x factorial times r minus x factorial. N minus r over n minus x is the same thing as n minus r factorial over n minus little n minus x factorial. The expression gets a little bit complicated, but you know how to compute these things using the factorial notation. And of course this one down at the bottom is big N factorial over little n factorial times big N minus little n factorial. Okay, so you can work all of those out using stuff that you already know. Okay, so let's consider this example of the use of hypergeometric distribution. Suppose a customer at a pet store wants to buy 2 hamsters for his daughter, but he wants 2 males and 2 females. That is, he wants only 2 hamsters in a few months. Okay, so he wants to choose hamsters of the same sex. All right, now, so if there are 10 hamsters, 5 male and 5 female, what's the probability of drawing 2 of the same sex? Okay, so does this fit our schema for hypergeometric distribution? Well, yes. Is it without replacement? Yes, because he's only going to draw 2 hamsters one after the other. He can't draw the same hamster twice. Okay, so and presumably each hamster has the same choice of being drawn, so it works that way. All right, so here we have 10 hamsters. And that's our big N is equal to 10. Okay. How many is he drawing? Well, that's going to be 2. So our little n is 10. I'm sorry, our little n is 2. Okay. Now, what do we count as success? Now, there are two ways he can be successful. Either he can draw 2 males, or he can draw 2 females. As far as he's concerned, one way of looking at it, if he's shooting for males, then getting 2 males is his success. If he's shooting for females, 2 females means 2 successes. Now, he really doesn't care if he gets 2 males or 2 females. In that case, both are successes. So we'll just take either one, and actually we'll have to add the 2 probabilities. Probability of 2 males plus probability of 2 females. Notice that these 2 are disjoint. They can't both happen. That's why we can sum the probabilities. Okay, so let's compute the probability of 2 males. Okay, so here we have big N equals 10, little n equals 2, and in this case, little r, if we're looking for a number of males, that's equal to 5. So in computing this eventuality, that the probability of males equals 2, I'm going to use these parameters. N equals 10, little n equals 2, r equals 5. So I'm computing here the probability that x equals 2. And if you go back to the formula on the previous slide and plug in the numbers, this is what you'll get. Okay. All right, so far I've talked about getting 2 males. If he's looking for 2 females, then each female is a success. You still have these same numbers. You get the same probability for 2 females. So the probability of 2 of the same sex, as I said before, you just add the 2 probabilities together, you get 0.44. That's the result. Have fun.